This is Lecture 5, Introduction to Bivariate Regression. By the end of this lecture, you should be able to understand the intuition behind bivariate regression, calculate the coefficient and constant for a bivariate regression, write out a regression equation, and conduct a significance test on a regression coefficient and constant. In the previous lectures, we discussed how we use statistics to determine if there's a statistical relationship between an independent and a dependent variable. Bivariate regression is one way in which we can determine the statistical relationship between two variables. It is called bivariate regression because there are only two variables in the regression, one independent variable and one dependent variable, hence bivariate. In order to demonstrate the intuition behind a bivariate regression, I'm going to use the following hypothesis as an example. As the strength of an upper chamber increases, the more control parties have over legislative candidate selection. In this example, strength of the upper chamber is the independent variable, and parties' control over legislative candidate selection is the dependent variable. To understand the intuition behind bivariate regression, imagine we plotted our independent and dependent variables on a graph. We placed our independent variable on the x-axis, strength of upper chamber, and our dependent variable on the y-axis, party control over candidate selection. Then we plotted the values for each observation on the graph. All of these dots here represent the individual observations. Next, imagine we drew a straight line that went through the middle of all of these points. Then we calculated the equation for this line. If you remember from your algebra classes, the equation for a line is y equals the slope times x plus the y-intercept. Remember, the slope tells you the steepness of the line. Or in other words, it tells you by how much y changes when x changes. The y-intercept tells you the value of y when x equals 0. And the line passes through the y-axis. You will calculate a similar equation for bivariate regression. However, we will make a few modifications. First, we will refer to our y as the dependent variable. We will refer to b, the slope, as the coefficient. We will refer to x as the independent variable. We will refer to a, the y-intercept, as our constant, and we will include an error term in our models. The error just tells us how far the individual observations deviate from this line. There is one final modification we make to the equation for a line in bivariate regression. We will place hats over y, b, a, and e to indicate that we are making estimates of y, b, a, and e. We cannot tell from a sample what the true y, b, and a, and e are. Instead, we make an estimate of what they are based on our sample. Now on to calculating b hat and a hat. These are the equations for calculating the coefficient b hat and constant a hat. In the next few slides, I will walk you through the steps of calculating the estimated coefficient b hat. However, I will briefly go through the equation here. In the numerator here, you are determining for each observation if the independent variable xi is deviating from the mean of the independent variable x bar in a similar/different direction and magnitude as the dependent variable yi is deviating from the mean of the dependent variable y bar. Although the calculation is a little different, this is very similar to the Pearson's correlation coefficient R. We're determining if the independent variable is deviating from its mean in a similar/different direction and magnitude as the dependent variable is. Now I'm going to walk you through the steps of calculating a bivariate regression. I strongly encourage you to have the b hat and a hat equations written on a paper next to you so that as I go through the steps it will make more sense. I will use the example from the beginning of the lecture in this demonstration. Recall that the hypothesis was, as the strength of an upper chamber increases, the more control parties have over legislative candidate selection. In this example, the strength of upper chambers is the independent variable x, and the party control over candidate selection is the dependent variable y. I gathered data on strength of upper chambers and party control over candidate selection for 11 countries from 1972 to 1990. In the end, I had 987 observations. I'm going to calculate a bivariate regression for this data, but I'm only going to show you the first 4 observations in the slide because I can't put all the observations on this slide. The first step in calculating b hat is calculating the mean of the independent variable x and the mean of the dependent variable y. You have to remember that the independent variable is x and the dependent variable is y, otherwise you will miscalculate your answers later on. So using the data from all 987 observations, I calculated the mean of the independent variable, strength of upper chambers, and it was 0.5. And I calculated the mean of the dependent variable, party control over candidate selection, and it was 4.21. The second step in finding b hat is subtracting the mean of the independent variable x from each individual x observation. In this case, this means you have to subtract the mean of strength of upper chamber 0.5 from the values of strength of upper chamber for each observation. So here we have 0.67. So 0.67 minus 0.5 is 0.17. And here we have 0.65. 0.65 minus 0.5 is 0.15. And we would continue doing this for each observation. The third step in finding b hat is subtracting the mean of the dependent variable y from each individual y observation. In this case, this means you have to subtract the mean of parties' control over candidate selection, 4.21, from the values of parties' control over candidate selection for each observation. So here we have a 6. 6 minus 4.21 is 1.79. And here we have a 2. 2 minus 4.21 is negative 2.21. We would continue doing this for each observation. The next step in calculating b hat is multiplying the corresponding values from steps 2 and 3. So here we have 0.17 times 1.79, which is 0.30. And here we have 0.15 times negative 2.21, which is negative 0.33. We would continue doing that for each observation. The next step in calculating b hat is adding all the values from step 4 together. After adding all of the 987 observations together, the value I calculated was 241.27. Note that this value is the numerator of the b hat equation. The next step is squaring the values from step 2. Recall that in step 2 we subtracted the mean of x from each individual x observation. We simply square those values. So for observation 1, xi minus x bar was 0.17, so 0.17 squared is 0.03. And for observation 2, xi minus x bar was 0.15, so 0.15 squared is 0.02. and you would continue doing this for the rest of the observations. The next step in finding b hat is adding all the values from step 6 together. After adding all of the 987 values together, the value I calculated was 117.23. Note that this value is the denominator in the b hat equation. The last step in calculating b hat is dividing the values from step 5, the numerator, by the values from step 7, the denominator. 241.27 divided by 117.23 is 2.06. So our slope or coefficient b hat is 2.06. Next we have to find a hat. A hat is a much easier calculation. A hat equals the mean of y minus b hat times the mean of x. Remember that I calculated these values earlier in the lecture slides. The mean of y is 4.21, b hat is 2.06, and the mean of x is 0.5. 4.21 minus 2.06 times 0.5 equals 4.21 minus 1.03, which equals 3.18. So our a hat is 3.18. So recall the regression equation is y hat equals b hat times x plus a hat. So using our estimates for b hat and a hat, our regression equation is candidate selection hat equals 2.06 times strength of upper chamber plus 3.18. Now after you calculate your regression equation, you can check to see if you did the math correctly. If we input the mean of x, or the mean of the independent variable, into the regression equation we calculated, the equation should equal the mean of y, or the mean of the dependent variable. The mean of x was 0.5 and the mean of y was 4.21. Our regression equation was candidate selection hat equals 2.06 times strength of upper chamber plus 3.18. So placing the mean of x, 0.5, here, we have candidate selection hat equals 2.06 times 0.5 plus 3.18, which is 4.21. And 4.21 is the mean of y. So why does the equation produce the mean of y when we input the mean of x into it? Because the regression line we calculate goes through mean of x, mean of y. This is the regression line that we calculated earlier. And this line goes through 0.5, 4.21. Remember from earlier in the lecture, I told you that regression takes into account if one variable varies from its mean in a similar/different direction in magnitude as the other variable. So it's not surprising that the regression line goes through the mean of x and the mean of y. Now recall from the beginning of the lecture, I told you that we use bivariate regression to determine if there's a statistical relationship between two variables. So how do we determine this relationship from the regression? The regression coefficient b hat tells us the impact that the independent variable has on the dependent variable. If the coefficient b hat is 0, that means the independent variable has no effect on the dependent variable. A slope of 0 means that as x changes, y does not change at all. Or, in other words, as the independent variable changes, the dependent variable does not change at all. However, based on our hypothesis, we do think the coefficient is different from 0. We expect it to be either greater than 0 or positive, or less than 0 or negative. If the coefficient is positive, then we say that as the independent variable increases, the dependent variable increases. Note that if this was the case, the coefficient or slope would be positive. That is why we would say there is a positive relationship. If the coefficient is negative, then we say that as the independent variable increases, the dependent variable decreases. Note that if this is the case, the coefficient or slope would be negative. That is why we would say this would be a negative relationship. So in order to figure out whether the coefficient is different from 0, we conduct a t-test. The first part of the t-test is writing the null hypothesis. In this hypothesis, we expect that the independent variable has no effect on the dependent variable. As the independent variable changes, the dependent variable stays the same. A more sophisticated way to write it is HO colon B hat equals 0. The H indicates that you have a hypothesis, the 0 indicates that it is a null hypothesis, and B hat is your coefficient. Stating this in words, you have the null hypothesis is that the coefficient is equal to 0. Next, you have to write your alternative hypothesis. You choose your alternative hypothesis based on your theory. If you expect that your independent variable has a positive impact on your dependent variable, your alternative hypothesis should be, as the independent variable increases, the dependent variable increases. The more sophisticated way to write this is H1 colon B hat is greater than 0. The H indicates that you have a hypothesis, the 1 indicates that it is an alternative hypothesis, and B hat is your coefficient. Stating this in words, we have the alternative hypothesis is that the coefficient is greater than 0. If, on the other hand, you expect that your independent variable has a negative impact on your dependent variable, your alternative hypothesis should be, as the independent variable increases, the dependent variable decreases. The more sophisticated way to write this is H1 colon B hat is less than 0. The H indicates that you have a hypothesis, the 1 means that you have an alternative hypothesis, B hat is your coefficient. So stating this in words, we have the alternative hypothesis is that the coefficient is less than 0. So recall our original hypothesis. As the strength of an upper chamber increases, the more control parties have over legislative candidate selection. And so we ran a regression on strength of upper chamber and party control over candidate selection. So the null hypothesis for our regression should be, as the strength of upper chamber changes, party control over candidate selection stays the same, or H0 colon B hat equals 0. And since we expect a positive relationship between strength of upper chamber and party control over candidate selection, our alternative hypothesis should be, as the strength of upper chamber increases, party control over candidate selection increases, or H1 colon B hat is greater than 0. After you write your null and alternative hypotheses, you conduct a significance test or t-test to determine if your B hat is different from 0. You turn your B hat into a t-score to determine if it is statistically different from 0. Here I will briefly explain why we are using a t-test to determine if our B hat is different from 0. Recall that most t-scores fall close to 0. All of these t-scores here are close to 0. As you can see, 0 is the most common t-score. As the peak of the histogram tells us, there are a lot of observations here. Once t-scores get somewhere between 1.6 units above or below the mean of 0, that is unusual. There aren't many t-scores that big or that small. Only 5% of t-scores fall beyond this point or this point. When we turn our B hat into a t-score, we can tell if the t-score is close to 0 in the t-distribution, meaning that the independent variable has no effect on the dependent variable, or far away from 0, meaning that the independent variable has an effect on the dependent variable. When we expect a positive relationship between our independent and dependent variables, we expect our t-scores to be positively different from 0. We say that it is positively different from 0 if the t-score has an unusually high value, about 1.6 units above 0. When we expect a negative relationship between our independent and dependent variables, we expect our t-scores to be negatively different from 0. We say that it is negatively different from 0 if the t-score has an unusually low value, about 1.6 units below 0. Okay, so now I'm going to show you how to conduct a significance test on t-tests on your BHAP. The first step is to choose your decision rule template. This is based on your alternative hypothesis. If you think your independent variable should have a positive effect on your dependent variable, your decision rule template should be, if the t-statistic I calculate is greater than the positive t value from table 6.4, the coefficient is greater than 0. Otherwise, it cannot conclude whether it is different from 0. Alternatively, if you think your independent variable should have a negative effect on your dependent variable, your decision rule template should be, if the t-statistic I calculate is less than the negative t value from table 6.4, the coefficient is less than 0. Otherwise, I cannot conclude whether it is different from 0. Note that we will be working with two t-values in significance tests. One is from table 6.4, and one you will calculate yourself. This is important to remember so you won't get confused. Also note that the values from table 6.4 are all positive. When we use this less than template, we have to put a negative sign on the t-value. As an example on how to conduct a significance test on a coefficient, I'm going to conduct a significance test on the b-half from our equation earlier in the lecture. Recall from the beginning of the lecture I had the following hypothesis. As the strength of an upper chamber increases, the more control parties have over legislative candidate selection. Based on this hypothesis, I expected there to be a positive relationship between my independent variable, strength of upper chamber, and my dependent variable, party control over candidate selection. The alternative hypothesis would suggest that the coefficient should be greater than 0. So the first step in determining whether this coefficient is greater than 0 is choosing our decision rule template. We choose our template based on our hypothesis. Since we expect a positive relationship between our independent and dependent variable, we choose the following decision rule. If the t-statistic I calculate is greater than the positive t value from table 6.4, the coefficient is greater than 0. Otherwise, I cannot conclude whether it is different from 0. Next, you have to choose the t-value you will use from table 6.4. You will choose a row and a column in this table, and the t-value that intersects that row and column will be the t-value you use. In order to choose your row, you have to calculate the number of degrees of freedom you have. The degrees of freedom equal the number of observations minus the number of independent variables minus 1. Recall that I had 987 observations in my analysis, and I had one independent variable. So 987 minus 1 is 985. So I look at the t-table under the degrees of freedom row, or column, for the 985 row. If the number is not listed, I choose the next lowest number. So there's no 985 row, so the next closest number is 120, so I'm going to choose the 120 row. Next, you choose the significance column. When conducting a significance test for coefficients, always start with the 0.05 column. Recall that we are determining whether our t-score is greater than 0 or within the 5% of t-scores that fall about 1.6 units above 0. 0.05 and 5% here are synonymous. Note that you can use the other significance columns in your significance test, but we will not be doing that in this lecture. When I look at the t-table and look for the t-score that intersects the 120 row and the 0.05 column, the t-score turns out to be 1.658. So I insert this value into my decision rule template. If the t-statistic I calculate is greater than 1.658, the coefficient is greater than 0. Otherwise, I cannot conclude whether it is different from 0. Step 3 in determining whether your b-hat is different from 0 is actually turning your b-hat into a t-score. The calculation is t equals b-hat minus 0 divided by the standard error of b. I already showed you how to calculate b-hat. I'm not going to go over how to calculate the standard error of b-hat. However, I will tell you the intuition behind the standard error and the t-test. The standard error tells us how well the independent variable predicts changes in the dependent variable. If the independent variable predicts changes in the dependent variable well, then there is not a lot of error. E-hat. The error is just the actual values of the dependent variable y minus the predicted value of the dependent variable from the regression equation that we produced, y-hat. Note that the error is in the numerator in the standard error of b-hat. So the smaller the error, the smaller the standard error is. Now note that the standard error is in the denominator of the t-score calculation. The smaller the standard error is, the smaller the denominator here is. And the smaller the denominator here is, the larger the t-score should be. This means we are more likely to get significant results as the t-score should be large and different from 0. In sum, when our independent variable predicts our dependent variable well, then our errors are smaller, our standard error is smaller, our t-score is larger, and we get significant results. Alternatively, when our independent variable does not predict our dependent variable well, our errors are larger, our standard error is larger, our t-score is smaller, and we do not get significant results. So now we are going to calculate our t-score. Remember that the b-hat from our equation was 2.06. I calculated the standard error of b-hat, it was 0.16. So 2.06 minus 0, and that value divided by 0.16 is 12.88. So now we compare the t-score we calculated to the t-score from our decision rule template. Remember that our decision rule was, if the t-statistic I calculate is greater than 1.658, the coefficient is greater than 0. Otherwise, I cannot conclude whether it is different from 0. The t-value we calculated was 12.88. 12.88 is greater than 1.658. Hence, we can say that our coefficient b-hat is greater than 0. We can reject the null hypothesis that the coefficient is equal to 0. Our conclusion is that our coefficient is positive and statistically significant. As the strength of an upper chamber increases, the more control parties have over legislative candidate selection. Note that if you were working with negative values that are significant, as in you expected the coefficient to be less than 0, you would say that the coefficient is negative and statistically significant. You would say as the independent variable increases, the dependent variable decreases. Also note that if in the test we just ran, if the t-score we calculated was not greater than 1.658, then we would have said that the coefficient was not statistically different from 0. We would have said that we could not draw any conclusions about the relationship between the independent and dependent variables. In this case, it is possible that the coefficient is 0 or greater than 0. We simply do not know. In other words, it's possible that the independent variable affects the dependent variable or does not affect it at all. We simply do not know. We would fail to reject the null hypothesis that the coefficient is equal to 0. Now I'm going to show you the significance test for a-hat, the constant. It is similar to the significance test for b hat. We want to know if a hat is different from 0. Except we don't have any expectations that a hat is positively different from 0 or negatively different from 0. So we run what is called a two-tailed t-test. Recall that in the t-distribution, most t-scores fall within 0. We are going to transform our a hat into a t-score and determine if the t-score is much higher than 0 or much lower than 0. In this case, we are going to determine if our t-score is within 2.5% of t-scores above 0 or 2.5% of t-scores below 0. Note that in having 2.5% in both tails, we are looking for a combined significance of 5%, as 2.5% plus 2.5% is 5%. So we're going to conduct a t-test where we look for t-values that are either positively different from 0 or negatively different from 0. The decision rule template for this t-test is, if the t I calculate is greater than the positive t-value from table 6.4, the constant is greater than 0. If the t I calculate is less than the negative t-value from table 6.4, the constant is less than 0. Otherwise, I do not know if it is different from 0. Now we need to find the t-value from table 6.4. This is similar to what we did before. We look for the t-score that intersects our degrees of freedom row and our significance column. Our degrees of freedom, df, are the number of observations n minus the number of independent variables p minus 1. Recall that I had 987 observations in my analysis, and I had one independent variable. So 987 minus 1 is 985. So I look in the table under the degrees of freedom column for the 985 row. If the number is not listed, which we know it isn't from earlier in the lecture, I choose the next lowest number, and we know that that next lowest number was the 120 row. Next, we find our significance column. In this lecture, we will use the 0.025 column for a significance test for a constant. We want 5% significance, so we look at the 0.025 column, or 2.5% in both tails. 0.025 and 0.025 is 0.05 or 5% in total. Since our degrees of freedom row was 120 and our significance column was 0.025, we have to look for the t-score that intersects the 120 row and the 0.025 column. And that t-score is 1.980. Inserting this t-score into our decision rule template, we have, if the t I calculate is greater than 1.980, the constant is greater than 0. If the t I calculate is less than negative 1.980, the constant is less than 0. Otherwise, I do not know if it is different from 0. Next, we calculate our t-score. The t-score calculation for a hat is similar to the t-score for our b hat. T equals a hat minus 0, and that value divided by the standard error of a hat. I will not go into detail on how to calculate the standard error of a hat. I just wanted to show you the equation. As you can see, it takes into account how well the independent variable predicts the dependent variable, as it includes the error term in its calculation. So applying this to our example, our a hat was 3.18 and the standard error of a was 0.10. So 3.18 minus 0, and that value divided by 0.10 is 31.80. So our t-score was 31.80. Recall that our decision rule was, if t is greater than 1.980 or less than negative 1.980, the constant is different from 0. Otherwise, I do not know if it is different from 0. Therefore, our conclusion is the t we calculated, 31.980, is greater than 1.980. So the constant is greater than 0 and significant. Note, if t was not greater than 1.980 or not less than negative 1.980, you would say the constant is not significantly different from 0.